Many liquids are essential in our daily life. They may include water, beverages, dairy products, chemicals, acids and bases, or pharmaceutical products. The quality of these liquids is determined by their chemical and physical properties. To assess these properties, various principles of measurement are used. One of these principles is the measurement of the chlorine content in liquids to assess the disinfection capacity. Disinfection destroys pathogens such as bacteria or fungi and prevents the spread of diseases. It is accomplished by applying either free chlorine or chlorine dioxide, ozone, or ultraviolet radiation to the water. Free chlorine, also known as hypochloric acid, is the most important disinfectant in water treatment, since it has a strong disinfectant effect, is almost odorless, and provides a depot effect. In 1908, John L. Leal, American physicist, developed the first regular chlorination of public water supply in New Jersey and could achieve a drastic decrease in waterborne diseases. Let's have a closer look at disinfection using free chlorine. The disinfection capacity and the chemical equilibrium of free chlorine depend on the pH value of the water. If the pH value is above 8, free chlorine is no longer sufficiently effective. At pH values below 4, even dangerous chlorine gas is released. The highest effectiveness of free chlorine is achieved between pH 4 and 8. A parallel pH measurement for compensation prevents distorted measured values. Free chlorine can be determined using the amperometric or photometric measuring principles. In the case of photometric measurement, a reagent is mixed with a water sample. This reagent reacts with the free chlorine, which results in a specific reddish sample color. The more free chlorine that is available, the higher is the color intensity. This color intensity is then measured based on the fact that the reddish color absorbs or attenuates light of a specific wavelength. Let's now concentrate on the amperometric measuring principle. An amperometric sensor usually consists of a gold cathode, also called a working electrode, and a silver chloride electrode that forms the anode. A DC voltage is applied to both electrodes. Cathode and anode are located in a reaction chamber that is filled with an electrolyte. A membrane separates the reaction chamber from the medium to be measured. The membrane is made of a superhydrophobic PVDF. It allows gaseous HOCl molecules to diffuse while it repels OCl ions due to their negative charge. The membrane shows a behavior similar to cell membranes of bacteria, for example. When the sensor is immersed in a medium containing free chlorine, the HOCl molecules diffuse through the sensor membrane and are reduced to chloride ions, Cl-, at the gold cathode in the reaction chamber. At the anode, silver reacts to silver chloride, releasing electrons. This results in a current flowing through the discharge system that is connected to the anode and cathode. This current is proportional to the concentration of free chlorine. The current is processed in the transmitter and displayed as concentration in milligrams per liter. When measuring free chlorine, the pH value must also be determined to compensate for the pH-dependent dissociation of free chlorine. If the pH compensation of the transmitter is activated, the pH value is included according to the preset curve and the transmitter displays true measured values. The amperometric measuring principle enables a continuous measurement of the chlorine content and requires very low maintenance. It helps to optimize chlorine dosing and reduces operating costs. Chlorine measurement is essential for safe water disinfection in many applications, such as legally required disinfection of wastewater, disinfection of drinking water, seawater desalination, in power plants, disinfection of packaged foods or cans and multiple-use bottles, and in swimming pool water. For further information on liquid analysis and chlorine sensors with MemoSense technology, visit the Endress & Hauser YouTube channel or endress.com.